So now we're going to take a look at testing for independence in a two-way table. Now we had previously been looking at one-way tables. A one-way table describes counts for the outcomes in a single variable. So if the counts are for a single variable, that's a one-way table, while a two-way table describes the counts for combinations of outcomes for two variables. So for instance here, we have two variables. One of them is whether the subject was in the treatment group or the placebo group, and the other variable is whether they were cured or whether they were not cured. And what we want to know is whether those two things are independent. Is being cured and being not cured independent of whether you were in the placebo group and didn't get the actual medication, or in the treatment group and did actually receive it? Because if those are independent, it means that whatever this treatment isn't working, is no better than the placebo. So we want to check for independence in this table, and we're going to use a chi-squared test, just like we did with the one-way table, except this chi-squared test, we're going to actually need to calculate the expected values a little bit differently. So to calculate those expected values, the first thing I'm going to need to know all the totals. So I find all the row and column totals. Once I have all those row and column totals, I'm ready to find the expected values. So obviously the row total is 35 plus, or the column total, 35 plus 21 is 56, 51 plus 28 is 79, 35 plus 51 gives me the first row total of 86, and 21 plus 28 gives me the second row total of 49. And this is the grand total. It's the total of this column, but it's also the total of this row. It's the total number of subjects. Total number of subjects. So we want to calculate the expected values. So I'm going to put all my expected values in this table. And to calculate the expected values, what we're going to do is for each cell, we're going to take the row total and the column total for that cell and divide it by the grand total. That's how I'm going to get the expected values here. So the expected count for treatment cured is going to be the row total times the column total over 135, which in this case, the row total is 56, the column total is 86. I divide that by 135. That's how I get that first expected value there, that expected count. Then for the next one, I do for 51, I'm looking at the row total is still 86, but now the new column total is 79. So 86 and 79 multiplied, divided by 135 is that second expected count. The third expected count, well, the column total is 56, the row total is 49, and I divide that by the grand total. And then the last one, once again, the column total is 79, the row total is 49, and I divide it by the grand total. So you can see how we get all those numbers. And then I just do my calculations there to get expected counts of 35.674, 50.326, 20.326, and 28.674. Those are my expected counts. Now that I have my expected counts, I can calculate the z squared for all these expected counts. So it's going to be the observed values minus the expected values squared. That difference has to be squared and divided by the expected value. So observed minus expected squared over expected. And these are going to be my different z values, z squared values I should say. And when you add up all those z squared values, we're going to get a chi-squared value. So all the totals, or all the values we get for these z squared, when we add them up, we're going to get a chi-squared test statistic. So these are the four different values. So my chi-squared test statistic then is just the result of adding all of those up. All right, so let's go ahead and find the chi-squared test statistic. All right, so let's give ourselves some space here. And we just need to add all four of these up to get the chi-squared test statistic. So this is the chi-squared test statistic, 0.06. So that means that this is our sample statistic. And we just need to figure out, it's also actually the test statistic. We just need to figure out this test statistic, what is the area to its right, so we can find this p-value. So in the sampling distribution, I have a chi-square distribution, and in order to figure out the degrees of freedom, we're going to take the number of columns and the number of rows and subtract one from each of those and multiply them by each other. So we're going to try to find what the sampling distribution looks like. So the degrees of freedom are the number of columns minus 1 multiplied by the number of rows minus 1. So that's going to be 2 minus 1 times 2 minus 1. I have 1 degree of freedom. So I have a chi-squared with 1 degree of freedom. That chi-squared kind of looks like this. And what I'm looking for is I'm looking for the area to the right of 0.006. So the chi-squared test statistic is 0.06, not 0.006, but 0.06. That's the chi-squared test statistic. And because this is a chi-squared test, I'm looking for the area to the right as the p-value. And of course, my null hypothesis is that there is no difference between the effectiveness of the treatment and the placebo. So basically there's no difference. There's no, they're independent of each other. And the alternative is that there is a difference. Obviously, if you're the drug manufacturer, you want the alternative hypothesis to be true. All right, so all we need to do is go to our chi-squared test statistic, the chi-squared distribution, and find the area to the left of 0.06. And that'll give me my p-value. So I can use Python to do this. All I have to do is use SciPy. So this is the code I'd need to run. I'd import scipy.stats as stats. And then because I'm looking for the area to the right, it would be 1 minus the chi-squared CDF with 0.06 as the chi-squared value, and 1 is the degree of freedom. So when you're using this chi-squared CDF, you need to give it the chi-squared value and the number of degrees of freedom. And we found the degrees of freedom to be 1, which is the number of rows minus 1 multiplied by the number of columns minus 1. This should be columns, not rows. They both say rows. It should be the number of rows minus 1 multiplied by the number of columns minus 1, not both rows. All right, so when we run that, we get this as our p-value. This is the area to the right. This is the area to the right. So once we have our p-value, we can then make a conclusion. So what would be the conclusion of this hypothesis test if the significance level was alpha equals 0.01? Well, I got this as my p-value, which means there's an 80% chance of getting a sample this extreme. That's a pretty high chance. So the p-value is greater than alpha in this case, and because the p-value is greater than alpha, I would fail to reject the null hypothesis. I would fail to reject because this is not a significant sample. This is not significantly different than just if they were independent. So then I cannot reject the hypothesis that they are independent and there's no difference between the effectiveness of the treatment and the placebo. So this drug company is going to be disappointed because my test just proved that their drug has no effect.